This is AP Calculus BC, and in this video we're going to talk about volumes again, but the difference today is that we're going to talk about volumes by a different method, and this method is called cylindrical shells. So the idea behind this method is that we can construct the volume of a figure in a different way than we did before. So last time when we talked about volumes, we were talking about cross sections. And that method works most of the time. However, there are some unique situations where that method of cross sections actually won't work or will be very, very difficult to implement. And so this second method that we're going to talk about here, called cylindrical shells, is basically the idea that we can break our volume into a bunch of really thin, concentric, cylindrical shells. And you can see in this diagram here, this sort of gives you the idea of what we're trying to do. So this has only got 5 shells, but you can imagine if you made the thickness of each one of those shells very, very thin and used an infinite number of those shells, then we could go from an approximation of the volume that I'm looking at in the image on the left to get the exact volume of that figure just by using those shells. So the whole idea is based on getting the volume of one of these cylindrical shells. Now, when we do this, it's a little bit confusing at first how this calculation works, but I want to explain what we're doing here. So take a look at one of these shells, and if you think about how we would find the volume of this shell, essentially what we're doing is we're taking the circumference of this cylinder. Well, the circumference would be 2 pi r, and you can see in this case we're calling the radius x. So we've got 2 pi x as the circumference. The height of that cylinder is f of x, and then the thickness of the cylinder is what's going to create a volume. So to create that volume now, we're going to use the thickness of that shell, and we're going to call that thickness delta x. So that would give me the volume of one of those cylindrical shells. Once we have one of them, then it's just a matter of using an integral to add up all of those shells to create the overall figure. Okay, so before when we did this, remember we were taking the area of the cross section and then we were giving it a thickness and then using the integral to add up all of those small cross-sectional pieces. So it's still the same general idea in that we're adding up a bunch of pieces, but now each one of these 2 pi x f of x delta x's is essentially a very thin cylindrical shell, and I can use the integral to add up all of those pieces over whatever interval I'm looking at. So I did want to show you an animation for this just so you can have in your mind basically what's happening when we go through these calculations. So here we're looking at 2 times the square root of x as the function, and you can see we're going from a to b, and what I want to do is I want to revolve this shaded region around the y-axis. Notice we have this vertical segment here from x up to f of x. That's going to show us what one of these shells would look like. So if I revolve this around, you can see that that vertical bar that I had there is now going to be one of my cylindrical shells. So it's got a radius, it's got a height, and then the thickness in this case would be delta x. So in the end, when we create the total volume and we do the integral, all we're doing is adding up an infinite number of those concentric cylinders to create that volume. All right, so let's take a look at a couple of examples. Once you understand how this works, it's actually fairly simple, but you have to get your mind wrapped around the idea of doing these volumes with a different method. Okay, so this first problem, it says find the volume of the solid of revolution formed by revolving the region bounded by x or y is equal to x minus x cubed and the x-axis from 0 to 1 about the y-axis. So when we go through and we want to calculate this, first of all, what I want you to think about is, let's say we were going to try to do this, we're revolving around the y-axis, let's say we were going to try to do this with the washer method. The issue that we would have with the washer method here, because you can think about how your washers, you would measure the inside radius and the outside radius. Well, the issue that we have is that the inside radius and the outside radius are actually being measured to the same curve. So there are some things that we might be able to do to work around that in certain circumstances, but there are situations like this one where we really don't have a good way to deal with that. So what we're going to do instead is use the method of cylindrical shells. Now, you're going to see on these diagrams a lot these rectangles. And these rectangles are just supposed to give you a feel for the thickness of the shell. And then you want to imagine that rectangle being revolved around in this case, the y-axis to create that volume. And when we do that, we have to have a couple of different measurements. We have to have a radius and we have to have a height. So my volume, when I do this with cylindrical shells, I'm always going to factor the 2 pi out because that's a constant value. So I need to do 2 pi times my radius. My radius in this case, you can see, is x. It's x units away from the y-axis. And then the height is just going to be the distance from the x-axis up to the function. So that would be x minus x cubed. And then my thickness of the shell is dx. So again, just to be clear on this, my 2 pi r is right here. 2 pi r times the height times the thickness. That creates the volume. And then again, the integral is going to add up all those pieces. So in this case, when I'm looking at my limits of integration, I'm thinking about the r values. What are my r values bounded by? Because x is my radius. They're going from 0 on the x-axis out to 1 on the x-axis. Okay, and in this case, if you solve that out, you would get 4 pi over 15. Okay, so fairly easy to do once you have a good feel for what are the measurements that we need to use this method. Okay, so here's another example. Now, this time we're revolving around a line other than the y-axis. We're actually going to revolve around the line x equals 2. So similar to when we looked at some of these volumes with cross sections and we did volumes by revolution, we have to make sure we reference what line we're revolving around when we measure our distances. So you can see here, we took this region and we revolved it around the line x is equal to 2. Okay, so when we revolve that, notice the way my radius is being measured. My radius is going to go from whatever point I am in the x direction to the line x is equal to 2. So this is actually my radius now, the difference between x equals 2 and whatever x coordinate I'm at. The height, though, is still the same. You can see the height is just being measured up to that function. So still kind of the same idea, it's just that I have to reference my radius in a slightly different way. So for my setup, I'm going to do 2 pi times my radius, which was 2 minus x, and then times my height, which would be x minus x squared, because that's the function that I'm revolving. And then I'm going to have a thickness of dx. And the only other thing I need here are my limits of integration. So the limits of integration are going to be determined by where is this region bounded. It goes from x equals 0 to x is equal to 1. And if you're not sure about why we're using 0 and 1, think about how that radius would be measured. When x is equal to 0, that would mean I'm measuring this distance from x equals 2 all the way to the y-axis. That would be a radius of 2. When x is equal to 1, that would mean I'm measuring the distance from x equals 2 to x is equal to 1, and I would have a radius of 1. So this 2 minus x is taking care of all of that for us by taking the fact that we're revolving around x equals 2 into account. All right, so when you solve this integral, you would end up with pi over 2. And again, notice that I'm factoring the pi out of the integral. Really, all my constants are being factored out of the integral, just because if I do this on the calculator, I want an easy way to get an exact solution in terms of pi. Okay, so we can also revolve around a horizontal line, and we can still do volumes by cylindrical shells. When we revolve around a horizontal line, that means that everything is now going to be written in terms of y. So the reason it's written in terms of y is because the thickness of our shell is now going to be dy. And I'll show you on this first example what I mean by that. It says, find the volume of the solid of revolution formed by revolving the region bounded by the graph of x plus y squared equals 16 and the y-axis about the x-axis. Okay, so first of all, notice that the thickness of that cylindrical shell is being measured in the y direction. That's like a delta y or a dy. So that's why I'm going to write my integral in terms of y. Now, this equation, x plus y squared is 16, is the same as x is equal to 16 minus y squared. And then my radius in this case, since I'm measuring from the x-axis up to that cylindrical shell, my radius in this case is going to be y. The height of this is going to be the distance from the y-axis out to that curve. So my radius this time, or excuse me, my height this time is going to be whatever that x-coordinate is, 16 minus y squared. Okay, so now when we find the volume here, we have to be a little bit careful with this. First of all, I'm going to do 2 pi. My radius is y. My height is 16 minus y squared. Thickness of that shell is dy. But think about your limits of integration here. If I were to go from -4 all the way up to 4 and revolve that around 2 pi in terms of the angle that I'm rotating, if I went all the way around 2 pi, I'm sort of doubling up on myself. So I've got to be careful with that, and I'm just going to go and revolve half of this region around so that I only have one revolution around the x-axis. So I'm just going to go from 0 to 4 to create that volume. And if you solve this one out, you would get a volume of 128 pi. So typically on our problems, we're not going to have area on both sides of the axis that we're revolving around because we run into things like this where we have to be really careful with limits of integration. But every once in a while, you might run into something like that. Okay, so there's one more example here that I want to show you. And this is one where we have a region that's bounded by 2 curves. So we are supposed to revolve this region between 4 cosine x and x minus 2 squared. We're supposed to revolve that region about the y-axis. So if you don't have the rectangles there like we were using as reference before, you can just put a vertical line in here, and that can help you think about how are you measuring the thickness and how are you measuring the radius, and also how are you measuring the height. So the height's going to be the distance between the curves. I can see that. My height is 4 cosine x minus the x minus 2 squared. My radius this time is going to be measured from the y-axis out to whatever position I'm at. So my radius is just x. And once I have all of that, the only other thing that I would need in this case are the limits of integration, because I would have to find that point to know where I'm going to stop. So I'm not going to show all of that, but on the calculator you could set 4 cosine x equal to x minus 2 squared, or you could just create this graph on the calculator and find the intersection point. But you would see these two graphs intersect at 0 and about 1.511. So for my volume, I've got my 2 pi. Inside the integral, I have my radius of x. And then for my height, I've got that entire expression, 4 cosine x minus the x minus 2 squared. And I'm integrating with respect to x. Remember, dx is the thickness of the shell. And I'm just going to go from 0 to about 1.511. Okay, so now at this point, clearly I've got an approximation because I've approximated that intersection point. So everything I do here doesn't really make sense to leave it in terms of pi. I still could, but as soon as I get into an approximated solution, usually I just want to write the whole thing out as a decimal. So this would be approximately 6.299 for my volume. Okay, so every time you do these, that's essentially what you're going to look for. You have to think about that cylindrical shell. Think about how you're going to measure your radius. Think about the thickness of the shell, because that'll tell you, do I want to measure in terms of x or y? And then think about how you're going to measure the height. And as long as you have those three things, it becomes pretty simple. Once you've done rotations about a horizontal and a vertical axis, you start to get a pretty good feel for what the setup's going to work out to every time. Now, one thing I want you to think about when you're going through the assignment is try to think about, would this be easier with cylindrical shells, or would it be easier with that disc washer cross-section method? Because sometimes one method is easier than the other. Sometimes only one of the methods will work. But there's going to be a lot of cases where you're going to be asked to find a volume, and you just have to decide which method you want to use. And the way you're going to figure that out is by thinking through the process of, how would this work if I did it with the disc or the washer method versus how would it work if I did it with the cylindrical shell method. So a lot of that is going to be stuff that you're just going to do in your head to try to think about how you would set each one of those methods up.